In this video, we will demonstrate the solution to our next projectile motion problem. Remember to look in the video description box for additional resources, and remember that if you find that the video solution moves too slowly, you can use the solutions document as a supplement or replacement for the video solution. All right, here's our next problem. You should pause the video and try this problem, and remember, as you're trying the problem, you should be trying to use the techniques we demonstrated in the previous video. Try to use the same method and notation and scratch work that we demonstrated in the previous video to try this problem. Remember, your goal is don't wing it. Have a systematic method that you're applying to the problem. Okay, well, I hope that you really did try this problem. You'll learn a lot more from the solutions if you're trying the problems on your own. And now we should go through this problem together. Well, the first thing we have to do is choose a problem-solving framework. Early in your class, the only framework you might have learned about is kinematics, which includes projectile motion, and that's what we can apply here. After the ball is hit and until the ball hits the ground, there will be nothing touching the volleyball. So for that interval, the only force on the volleyball will be the force of the Earth's gravity. And that's the criterion for applying projectile motion. So we've already completed our first step from our systematic projectile motion approach. We saw that this does involve projectile motion. Nothing is touching the volleyball, so the only force on the volleyball is the force of the Earth's gravity. The object that is experiencing the projectile motion is the volleyball, and the interval of time during which it experiences projectile motion is after the volleyball is hit and until the ball hits the ground. Of course, once the ball hits the ground, it'll be touching the ground, and then it'll feel a force from the ground, and at that point, it'll no longer be experiencing projectile motion. I hope that you've already printed out this handout. If not, you should print out the handout right now. And remember, you should have that in front of you as you're trying the problems and watching the video solutions. The link to this is in the video description box. Something else you should print out, remember that there is a problems document with all the problems we're covering, and you should definitely print out that document even if you're watching the video solutions, and here's why. It's very important to always be able to reread and re-examine the problem at every point in your solution. But while I'm solving this problem in the video, the problem is going to move off the screen sometimes. So you'll get a lot more from the video if you can always consult the problem in front of you on a piece of paper. So please print out that problems document and have this problem printed out in front of you so you can consult it whenever you need to during your solution or while watching the video solution. Let's move on to our next step, checking the units. These first units here we see might be a little mysterious to some people, so let's review what those units mean. So you should know that anything q to the negative p power, that means 1 over q to the positive p power. That's what negative exponents mean. This is how you interpret a negative exponent. So for example, if we have s to the negative 1, that means 1 over s to the positive 1, which is the same as 1 over s. So if we have meters times s to the negative 1, that's meters times 1 over s. And we can multiply across to see that that's meters per second. All right, maybe a lot of you already knew that, but it's good to understand that these units mean the same exact thing as these units. So you should recognize that these two types of units are the same thing. You could read this as per seconds. So this really is meters times per seconds, which could be interpreted as meters per second. All right, well, those are the SI units for velocity. Those are the SI units for velocity, and these are also SI units for measuring distances. If you weren't familiar with this notation for units, it would be good to make a note of how to interpret this negative exponent. I think some students have forgotten from high school how to interpret negative exponents, so this might be a refresher. Professors like to write the units this way sometimes because this way they can avoid writing the units as a fraction. This step does not apply because this is for symbolic problems, and the problem we're working on is a numeric problem. The information is given in numbers, so this step does not apply. We want to start our sketch by drawing the object's path. Now you should have memorized that for projectile motion the path is a parabola. So let's go ahead and draw that path. So we might draw the path like this. Notice that this path is different from the path from the previous problem. In the previous situation, the object started moving upwards, but here the object is already moving downwards when the projectile motion begins. So do you see, this would be a poor drawing of the path because this has an upward and a downward component, but this problem, the object only moves downwards. So we're only using part of the parabola. We're not using the left part of the parabola, only the right. And in fact, this would still be a poor drawing. We shouldn't even include the peak of the parabola. Now the way to think about this is remember that the velocity vector at a point in time should be tangent to the path at that point in time. So the initial velocity here is downwards. The initial velocity is downwards. That means the tangent at our initial point should be downwards. So we don't want to start like this because here the initial tangent would slope upwards. That doesn't match what we know. And we don't even want to do this where we include the peak, because if we start from the peak, then the initial tangent would be horizontal. But we don't want the tangent to be horizontal, we want it to be downwards. So we have to include just this portion of the parabola so that the initial tangent is downwards, just like the velocity here is downwards. Okay, so this is the correct picture because this allows us to draw the tangent at the initial point at a downward angle of 15 degrees below the horizontal. And remember, what's the 15 degrees? Is this the 15 degrees? No, it's not 15 degrees with the path. It's 15 degrees between the horizontal and the initial velocity vector. Also, as discussed in the previous video, always label everything you write down. So we want to label this as our initial velocity vector. This is the symbol for the magnitude of the initial velocity vector, and we know that magnitude is 17 meters per second. Okay, so to review, how did we know which part of the parabola to draw here? Well, remember that the velocity vector at the initial point should be tangent to the parabola at the initial point. We knew here that we wanted a downward velocity vector at the initial point. That means a downward tangent at the initial point, and this is the type of curve that allows us to draw that tangent. Okay, so we drew the object's path. We should now start to build. Notice that the path is the path is a parabola, but that doesn't mean we use all parts of the parabola. Here we're missing the left part and even the middle of the parabola, so to speak, and we're just using a portion of the right side of the parabola, so to speak. Now we want to start building as much information as possible into our sketch. Well, we were given this horizontal distance, so let's build that information into the sketch. Is this a good way to build into the sketch? No, because I didn't include the units. This symbol here doesn't make much difference, but we can also include that. Is this a good way to build this into the sketch? Well, no, because I didn't say where this distance begins and ends. Here's a good way to build it into the sketch, showing where the distance begins and ends. Okay, so we've built that given distance information into our sketch. Next step, let's write down the key points in time. I would say that there are 2 key points in time in this problem. Here's one. And and we can generally set the first point in time in the problem equal to 0. So I'll do that, and I'll say this is the second key point in time. So I'll call that t sub 1. Why are those the key points in time rather than any of these other points in the middle? Well, this is a key point in time because we are given information about it, this distance. This is a key point in time because we're given information about it, like this velocity, and also we'll soon see that the question is also asking about this point in time. It's asking about the height at this point. Whereas the other points in between, we're not given any information about them, nor does the question ask about them. So those would be good choices to pick as our key points in time. Now we need to write down our axes. For a projectile motion problem, we want to pick usually up and to the right. Don't just mentally identify the axes. You should always, in physics problems that deal with vectors, write your axes down on paper. In particular, we need these axes whenever we're dealing with vector components. So we wrote down our axes. Since we're going to be dealing with position, we need to choose an origin for position. And as we discussed in the previous video, usually for projectile motion problems, we want to choose the lower left corner of the sketch as our origin. And again, we should actually write that down, not just think about it. This is the lower left corner. So here's our origin in the lower left corner. Why is this the lower left corner? Well, this point is the furthest left that we care about in this problem, and that's how far left our origin is. And this point is the lowest down that we care about in our problem, and that's also how low down on the page the origin is. So that's our lower left corner. This is the point where the position coordinates will be 0 and 0. So we wrote down our origin. You should actually write that down on your sketch. Now we're ready to label the position coordinates. So our coordinates here will be x0 and y0, and the coordinates here will be y1 and x1. Can we put in some specific numbers for those? This point has the same horizontal position as the origin, so the horizontal coordinate is 0. And I don't think we know the vertical coordinate. This point is 5.8 meters horizontally from the origin. So its horizontal coordinate is 5.8 meters. Remember, when you write a number by itself, don't write it like this. Always include units. And this point has the same vertical position as the origin, so the vertical coordinate is 0. All right, so we've put as much labeling as we can into these coordinates. So remember, the purpose of choosing the origin is to help us write down position coordinates. We don't use the origin for analyzing velocity or acceleration. We only need the origin for position. Notice that on this problem, we did not choose the initial point on the path as the origin. And maybe you can see that would be bad. Do you see why this would be a poor choice? Do you see why this would be a poor choice as the origin? Well, if we choose this point as the origin, but we still choose these axes, well, then this y-coordinate would be negative. Well, when possible, we'd like to avoid negative numbers in the problem, and that's why this is not the best choice as the origin. And that gives you an idea for why when we're choosing these axes, it's best to choose the lower left corner of the problem as the origin, because then none of the points will be negative relative to the origin. So the origin is not necessarily the initial point on the path. The best origin for projectile motion problems is usually the lower left corner, as we've demonstrated here. So we completed this step of labeling the coordinates for position, including specific values when possible. Now we're ready to identify the question. Well, right now we're working on part A. It's good to identify the question with a question mark and a specific symbol. So here's the symbol for what the question is asking us in part A. But when possible, we want to build that question into the sketch. All right, so now we've shown that what the question is asking us for is the distance from here to here, which the problem tells us to symbolize with an H. It's really crucial on all physics problems to try to clearly identify what the question is asking you for. And it's good to write that down. Identify it with a question mark, try to pick a specific symbol for the question, and if possible, build it into your sketch. So we identified the question with a question mark and a specific symbol and built it into the sketch. Now we're given the velocity in this problem, so we need to break that velocity into components. Now let's be careful about that. If you read carefully, the problem doesn't mention velocity. The problem gives us the initial speed and the initial angle of movement. So if we have the speed and the angle of movement, why do I say that we have the velocity? Well, here's why. The object's speed tells us the magnitude of the object's overall velocity vector. And the object's direction of movement tells us the direction of the object's overall velocity vector. So in this problem, we were given the initial speed, and therefore that also tells us the magnitude of the object's initial velocity vector. We were also given the initial angle of movement, direction of movement of the object. But if you know the object's direction of movement, then you know the direction of the velocity vector, according to these rules. So even though the problem didn't mention velocity, it gave us the exact information we need to know the magnitude and direction of the velocity vector. Remember, velocity is a vector, so it has a magnitude and a direction. All right, I actually already took all these ideas for granted when I already drew the velocity vector here. I already assumed that this angle and this magnitude represent the magnitude and direction of the velocity vector, and I've already built them into the sketch. Remember, I used that information to draw the parabolic path correctly. We knew that at the initial point, the velocity vector should be tangent to the path, and based on this information, that meant that the initial velocity vector should be downward sloping. So we've really already taken these ideas for granted in our solution. All right, so this is the magnitude and direction of the velocity vector, and now we need to break that into components. The way to do that is to draw a right triangle, but we should not do that in the main picture because that would make the main sketch too messy. So let's redraw this initial velocity vector in a separate picture. All right, so I've redrawn the velocity vector, taking it out of this picture and drawing it down here. Now we need to draw a right triangle, in which the overall vector represents the hypotenuse and the legs are the components. Here's that right triangle. Remember, we always want to label everything we write down. What's the correct label here? Well, this is the x component of the velocity, and this is the y component of the velocity at time 0. Why did I use slightly different symbols here for x and y components? Well, as we discussed in the previous video, in projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. Since the horizontal velocity is constant, we don't need a time subscript to indicate the horizontal velocity at different times. Since the vertical velocity is changing, we do need a time subscript because the vertical velocity here is different at different times. Now remember, we need arrows to show the directions of these components. Well, the overall vector is pointing down and to the right, and that means our components should be pointing down and to the right. Now, before we figure out the magnitudes of these components, let's follow the process that I talked about in the previous video and write down the signs on the components. Well, the horizontal component is pointing to the right, which is our positive direction. So I'll put a plus to show that this component is positive. Now, the vertical component here is pointing down, but down is our negative direction. Now you can see why we needed the axes. We need the axes when we deal with vector components. We need the axes to figure out the plus and minus signs on the components. Well, this right here is where people are most likely to make a mistake on this problem. The most common mistake people make on this problem is they forget that the vertical velocity is negative. So I hope you got that right when you tried the problem. You're more likely to get that right if you figure out the plus and minus signs before you figure out the magnitudes. Now let's go ahead and figure out the magnitudes using our SOHCAHTOA equations. I'll label that this side is the hypotenuse because it is opposite from the 90-degree angle. This side is adjacent. What does adjacent mean? Adjacent to who? The adjacent side is the side that's adjacent to the angle that you're focusing on for this problem. Are we focusing on this angle in this problem? No, we're focusing on this angle. Well, this side is adjacent to the 15-degree angle that we're focusing on. And I'll label this side as opposite because this side is opposite to the 15-degree angle that we're focusing on. Of course, if on a different problem we focused on this angle, then we would label different legs as opposite and adjacent. Who is opposite and who is adjacent depends on which angle you're focusing on. Now, we're going to use sine and cosine to get our equations here, not tangent, because we want to use the number from the hypotenuse, and the tangent doesn't deal with the hypotenuse. So this stands for sine of the angle equals length of the opposite side over the length of the hypotenuse. So and this stands for cosine of the angle equals length of the adjacent leg divided by the length of the hypotenuse. Ka. So now we can plug in. The opposite side here is our V naught y. The hypotenuse is 17. Cosine of the adjacent side here is Vx. And hypotenuse is 17. Now, why did I use absolute value signs here? Well, I explained that in the previous video. Remember that this stands for the length of the opposite side, which could never be negative. So I don't want to use this symbol because a component could theoretically be negative, so it can't represent a length. I want to use absolute values. Absolute values can never be negative, so they're a more appropriate symbol for representing a length. And in fact, in this problem, that makes a big difference because actually this component is negative, so it really is wrong. It's really wrong to use this symbol in the SOHCAHTOA equation because we can't use a negative value to represent a length. So it really is more accurate to use the absolute values here. It doesn't matter that much on this problem whether we use absolute values for Vx because Vx is positive anyway. But what I'm trying to convince you of is that these are the better symbols to use in general. When you do the SOHCAHTOA equations, it's best for a beginner to always use absolute values. Because absolute values could never be negative, and so they're a better symbol to represent lengths, which could never be negative. Now we're ready to solve these equations by multiplying both sides by 17. As we try to get the variable by itself. Now we're ready to do the calculation on our calculator. 17 times sine of 15 degrees and 17 times cosine of 15 degrees. Remember to make sure that your calculator is in degrees mode. Now we're going to round these numbers off. How much should we round them off? Well, all of the numbers here the original numbers here had 3 digits. So most professors would accept if you round it off to 3 digits. 2 digits might be insufficiently precise. So I'll round this off to 3 digits because this is a 9. This is a little tricky because this is a 9, we want to round up this digit. But because this digit is also a 9, it turns into a 0, and we have to round up this digit. So this rounds off to 4.40. If we want to round this to 3 digits, it rounds up to 4.40. I'll just write that as 4.4 just to keep the math a little bit simpler. And over here, we'll round this off to 16.4. I hope that you're saying that this is not a great way to write this. As I discussed in the previous videos, when you get an equation down to a single number, you should always put the units back in. The SI units for velocity, you should know, are meters per second, so be sure to put the units back in. I discussed this issue of how aggressively to round your intermediate figures in the previous video. So like I said, I'm not going to try to figure out what the best number of digits to keep in a real-life experimental setting is. I just want to kind of keep maybe the fewest number of digits that would be good enough to get full credit on an exam problem, because the main purpose of these videos is to help prepare you for exam problems. So in a problem like this, like I said, the professor might not want you to keep only 2 digits, since the numbers had 3 digits, but the professor would probably accept if you were keeping 3 digits. It's certainly okay to keep 4 or 5. If you want to keep 4 or 5 digits, that's okay, but it does clutter up your math and make the math a little bit more complicated to work with. So this is probably the simplest and most aggressive amount of rounding that professors would generally accept. So that's what I'll stick with for this problem. Let's see, going on. We should always, when we get intermediate results, check if your answers make sense. Oh, actually, we're not ready for that yet, are we? We actually haven't finished because we haven't actually figured out the components. Remember, these are only the absolute values of the components. That's what these symbols remind us. So the symbols remind us we need another step. We need to actually figure out the complete component, including the sign. Well, we already figured out the signs. The vertical component is negative, and the horizontal component is positive. Now, as I said, this is the part of the problem that students, are most likely to get wrong. The most common mistakes I think students would make on this problem is leaving out the negative sign on the initial vertical velocity. If you leave out this negative sign, you'll plug the wrong number into your kinematics equations and you'll get the wrong answer. So this is a serious issue for doing well on this problem. Okay, so let me ask you a question. When you tried this problem, did you remember to put a negative sign in front of v naught y? If you did remember to put a negative sign here when you did the problem on your own, good for you. That shows that you're making good progress on being aware of the signs for components. On the other hand, if you forgot to put in this negative sign, you need to ask yourself, what are some techniques that you could use to do better on that in the future? One of the most common mistakes students make throughout their physics course is forgetting the negative signs on negative components. Well, to review, here's the techniques that can help you with that. Remember that when you draw your right triangle, draw the arrows on the components, because that's what tells us the plus and minus signs. Remember, it's best to figure out the signs first before you figure out the magnitudes. If you do the magnitudes first, you might forget about the signs completely. Also, I think maybe from this problem now you can see why using the absolute value signs is a good idea when you do the SOHCAHTOA equations. The SOHCAHTOA equations are about lengths, and lengths can never be negative. That means the SOHCAHTOA equations will not tell you the signs of the components. They only tell you the absolute values of the components. And we should remind ourselves of that by using absolute value symbols when we work with the SOHCAHTOA equations. If you use an absolute value symbol in the SOHCAHTOA equations, that will automatically remind you that you're not done after the SOHCAHTOA equations and that you need one more step where you put in the sign for the complete component yourself. In fact, I think that's what actually happened to me myself when I was going through this video. I was about to say that we were done when we got to this line, but then I saw the absolute value symbols and I realized that I wasn't done. I had forgotten to put the plus and minus signs in. One more thing. As I discussed in the previous video, I know that in most contexts, you're probably not used to putting positive signs in front of positive numbers. But I strongly recommend that in physics, you should put a positive sign in front of positive components. Whenever the component could theoretically be negative, if it's positive, it's good to emphasize that with a positive sign. And one reason for that is if you remember to put the positive signs in front of positive components, you're just much more likely to also think to remember to put the negative sign in front of negative components. So we've gone over actually a bunch of different techniques that if you use those techniques, I think you'll be much more likely to remember the negative signs that you need on negative components. And like I said, that's a big issue. A lot of students lose a lot of credit on their exams because they forget those negative signs on negative components. So take that issue seriously and try to use the techniques that we've been illustrating in this video, especially if you originally got this problem wrong because you forgot this negative sign. All right, now we're ready to ask if these intermediate results make sense. And a good way to do that is to build them into our right triangle sketch. So our x component was positive 16.4 meters per second. And our y component was negative 4.4 meters per second. Now notice that in this right triangle, the vertical component was drawn much shorter than the horizontal component. And we can see that our results match that. You can see that the magnitude of this vertical component really is much less than the magnitude of the horizontal component. And that's consistent with the idea that this length is much less than this length. Now, this only works because we drew the 15-degree angle roughly to scale. 15 degrees is a pretty shallow angle, so we drew this vector as sloping at a pretty shallow angle. So if you draw that roughly to scale, then these lengths should also be roughly to scale, and then we can check whether these numbers make sense. I know that you're never going to get this angle perfectly, but the point is this is a pretty shallow angle. So if you drew a pretty shallow angle in your right triangle, you'll get that the horizontal leg should be considerably longer than the vertical leg. And then we can check that that really does agree with the numbers that we got by doing the math. All right, so these answers do seem to make sense. Another way they make sense is that both of these numbers are less than the hypotenuse. And that has to be the case, right? The legs have to be less than the hypotenuse. That's a rule of geometry. If either of these numbers had come out to be bigger than 17, that would violate the rules of geometry, and we would know we'd made a mistake. So it's always good to try to pause and ask whether your intermediate results make sense. That way you can catch mistakes before you proceed with the rest of the problem. So we've completed this step. We broke the velocity into components, and the big thing we saw here is remember to watch out for the plus and minus signs on the components. That's the big issue on this problem. Now for our next step, we want to label the initial and final positions on our path. I'm going to choose time 0 as our initial point. Let's choose time 0 as the initial point and time 1 as the final point. And you should always label those in your sketch. These are the 2 points that we're going to plug into our projectile motion equations. And those are a good choice. This is a good choice because we were given information about this point. We were given this distance. And this is a good choice to plug into the equations because we were given information about it, this velocity, and because the question is asking about it, this height. So we've figured out the initial and final positions on the path. Now we're going to write down our setup. This step is the same for pretty much any projectile motion problem, so let's actually carry out that step. So here's the setup for our x component. The setup for the x component is a single equation because we already know the equation we're going to use for the x component. The setup for the y component is different. It's a listing of 6 variables. We don't know which equation we're going to use for the y component yet, so the best way to organize our thinking for the y component is just to list the 6 variables. Now, we should always, for a projectile motion problem, write down this acceleration. Projectile motion is when the only force is the force of the Earth's gravity. 9.8 meters per second squared is the magnitude of the acceleration due to the Earth's gravity. And the Earth's gravity pulls objects downward, which is our negative direction. So that is why we need this negative sign. Just like you'll get this problem wrong if you leave out this negative sign, and you'll also get the problem wrong if you leave out this negative sign. By the way, I'm assuming here that you're using up as your positive direction. If we have chosen up as the positive direction, then we need this acceleration to be negative and this component to be negative. It's acceptable to choose a different positive direction. If you wanted to choose down as your positive direction, then these two things would not have to be negative. Some people might prefer that type of solution. This is the way I think most textbooks, though, would solve this problem. And maybe it's the best way for beginners to learn. Maybe it's best for beginners to be consistent in all projectile motion problems, like most textbooks are, and just always choose up as your positive direction. If you do that, then this component has to be negative, and this component has to be negative. Okay, but the signs on your components depend on the axes that you choose. That's why we need to write down those axes. So this is our setup. I think I've also recommended that we should connect these two with an arrow. Why is the setup for the x component so different from the setup for the y component? You should know the answer to that because I discussed that in the previous video. As we've already mentioned in this video, in projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. That's a very big difference, and because of that big difference, we have to treat the x component setup quite differently from our y component setup. I talked about the reasoning behind that more in the previous video. Here's our setup. So we've completed this step. It's really crucial to actually write down this setup for every projectile motion problem. Don't skip this step. This is the key. This step right here is the key to this entire method. All right, now we want to, in the setup, we want to indicate the question with a question mark. Well, the question here we know was asking for h, but how does that relate to our setup? Well, we should be able to see now that when we know this vertical coordinate, we will know the answer to the question. Because this vertical position is 0, since this vertical position is 0, this distance of h is also equal to the position coordinate right here. So when we know y initial, when we know this position, we're also going to know that that same number represents this distance. And so the specific symbol we're going to use for y initial on this problem is capital H, because that's the specific symbol the problem told us to solve for. Okay, so previously we had built the question into our sketch with a question mark, and now we go further and we build the question into our setup with the question mark. And we also found the specific symbol we were using for the question, which was again capital H. Now we're ready for our next step, which is to write down our numbers or specific symbols for the remaining variables using the work we've already done. X final, that's going to be 5.8 meters. X initial is 0. Vx, well, that's the number that we worked out up here, 16.4 meters per second. Delta t, we don't know, so I'll just continue to write down this symbol, delta t, for that. Y final is 0. V initial, well, that's the number we worked out here. And here's where that negative sign is crucial again, negative 4.4 meters per second. Over here, we're writing numbers by themselves, so I am going to include the units, as you should always do in physics when you write a number by itself. Over here, I'm plugging numbers into an equation, so I'm leaving the units out to make the math simpler. All right, and then we have v final y over here, and we don't know what v final y is, but we can write down a specific symbol for it. The most specific symbol we can use on this problem for v final y is v sub 1y, the vertical velocity at time 1. All right, so we started with our general equation and symbols for the setup, and then we plugged in specific numbers and symbols for this problem. So we've completed this step of writing down specific numbers and symbols for our remaining variables. Now in the next step, we have to decide whether we should be working with the x or the y component. Well, the question is asking us about the y component, but so far we only know 3 y numbers. We only know 3 y numbers, but that's usually not good enough. You can see that you usually need to know 4 y variables before it's helpful to pick a y equation. So we'll have to postpone our work here on the y variables. But that's no problem. We'll just shift over to the x component. On the x side, we have one equation with only one unknown. So we can solve for this unknown, and then we can plug that back into the y component, and that'll help give us more information to solve the y component. So let's go ahead and solve this x equation. First, I'll make an easy simplification. And then it should be easy to solve this equation by dividing both sides by 16.4. We want to get the delta t by itself. Time for the calculator. 5.8 divided by 16.4. All right, and as I discussed on this problem, the numbers were given with 3 digits, so the professor would probably be thinking it acceptable to round off our intermediate results to 3 digits. So I'm going to round this off to 0.354. Because this is a 6, this gets rounded up to a 4. I hope you're saying that we need units. When we get down to a single number, we should put in the units. The SI units for time are seconds. Since all the numbers we input were in SI units, we can trust that our output is in SI units. It's probably best to leave the units out when you plug into the equation, but put the units back in when you get a single number. All right, and again, since we have an intermediate result here, we should pause to ask, does this intermediate result make sense? Well, first of all, this is positive, and that does make sense. If this had come out to be negative, that would indicate a mistake. The time that elapses shouldn't be negative. Now, you should be a little worried maybe that this is so small. We don't usually get such small times. Does that make sense on this problem? Well, remember what's happening here is that a volleyball player is hitting a ball towards the floor. And if you think about it, if you hit a ball towards the floor, it might not take very long for that ball to hit the floor. It might easily take less than a second if you hit a ball towards the floor for it to hit the floor. So actually, this is maybe fairly reasonable. This is a pretty short amount of time, but when you hit or slam a volleyball towards the floor, it actually could hit the floor maybe in quite a bit less than a second. So this seems to be possible. If it had come out to be 0.03 of a second, that would seem definitely suspiciously small, and we would think we'd made a mistake. And certainly, if it came out to be 3.5 seconds, that actually seems too long for a hit volleyball that's hit down to hit the ground. And certainly, if it had come out to be 35 seconds, that would be way too long, and we'd be confident we made a mistake. So let me ask you a question. When you got this number, did you pause to ask if it made sense? This is a very small amount of time, so you certainly should have paused and asked yourself whether a fraction of a second made sense on this problem. I know that's a difficult skill, but the more you practice, the better you'll get, and The upside of that is you'll get a better understanding of the material so that you're not just kind of mindlessly plugging into equations to solve the problems. And also, that gives you a way to catch the mistakes that you might make on your exam. So if you didn't think of whether this small amount of time made sense when you did the problem before, I encourage you to try harder to use that technique in the future. Okay, so now we're going to take this number and plug it into our y component. This arrow reminds us that that was our strategy all along. Again, never write a single number by itself without the units. Okay, now remember we said that when we knew 4 y values, we would be ready to pick a y equation. And now, with the addition of the delta t, we do know 4 y values. So it's time to pick a y equation. We know 4 y values, so now we can pick a y equation. Here on the handout are our options. Now, which equation do we want? In the previous video, I discussed the fastest way to figure that out. Which is the one variable here that we don't care about? Well, we care about these 4 variables because we want to plug those numbers into our equation. And we care about this variable because this is what we're trying to figure out. So the one variable that we don't care about so far, is this one, v final y. So we want to pick the equation that's missing v final y. And the handout is set up to make that easy. Here's the equation that's missing v final y. By the way, this is the equation that's used by far the most often in projectile motion. That's why I wrote it first in the handout. You'll use this equation a lot more than the other two. Let's start by writing that equation down. Y final equals y initial plus v initial y delta t plus 1/2 a sub y delta t squared. And now we can use the setup to plug in. I hope you can see how this setup really pays off for us here. It's organized all the data of the problem so that we can easily get the numbers that we need to plug in. Our y final is 0. Our y initial is h. V initial y, negative 4.4. Here's one way we could plug that in. And here again is where it was crucial that we figured out that this component was negative. If we hadn't figured out that this component was negative, we would plug in a positive 4.4, and obviously that would give you the wrong answer when you went through the math. Our delta t is the new number that we figured out, 0.354. A sub y is negative 9.8. Can't forget that negative sign as well. And the delta t again, 0.354. Don't forget to keep copying this square. Remember the advice I gave you in the previous video. Write the general formula before you plug in specific numbers and symbols. Do not just write this down. Don't go straight to here. Instead, write the general formula first, then plug in. That's the best advice for beginners who have difficulty with the problems. I think we're ready to use our calculator to simplify our math. Many students might split up this calculation into multiple steps on the calculator. That's okay if you want to do it that way. But if we have written the math correctly on the page, and if we type it into the calculator exactly the same as it looks on the page, then we can trust that a scientific calculator will give us the correct answer in one step. What should I do now? Before I click enter, I better go back and check that I plugged this into the calculator correctly. Always double check everything you put into the calculator before you hit enter, or at the very least after you hit enter. All right, hopefully I got that correct. Again, I'm going to round off to 3 digits. This equation is easy to solve. Well, this isn't good. When we get a single number, we should put in the units. The SI units for height are meters. So let's put in those units. Okay, well now I think we've completed this step. Notice that first we used the x component to find delta t, then we plugged that value into the y component, as you will usually do on two-dimensional projectile motion problems. That's the meaning of this arrow. So it looks like we're ready to write our answer for part A. Is this a good answer? Nope, this is terrible. This should be marked wrong, and answer without units is wrong. Remember to include the units. Now, before we move on, we want to make a series of checks. I already checked that I included the units. We should check that we've answered the right questions. Let's go back up to the problem. They were asking for the height from which the ball was struck. So yeah, it looks like we've answered the correct question. Have we answered all parts of the problem? Well, we've answered all parts of part A, but hopefully now we'll remember that there's still part B that we're going to have to get to. Now we should also ask, does our answer make sense? And for this, again, it helps to remember what the question was asking us. The question was asking us for the height that a volleyball player hits a volleyball from. A downward hit on a volleyball. So is this a logical height that a volleyball player might hit downwards on a volleyball? Well, first of all, let's think about positive or negative. This came out positive, which is logical for a height. If this math had come out negative, that would tell us we'd made a mistake. It doesn't make sense for this height to be negative. What about the size of this height? So we're just going to check this roughly. So first of all, I'll say that 2.17 meters is roughly 2 meters. As I discussed in the previous video, people in the US might be more comfortable working with yards. And roughly speaking, a yard is roughly the same as a meter, so this is about 2 yards. Is this a reasonable height to hit a volleyball from? Yes. It might help you to remember that 1 yard is exactly 3 feet. The number of feet is 3 times the number of yards. So 2 yards is 6 feet. So what we have here is actually this person is hitting the volleyball from a height that is somewhat greater than 2 meters, so maybe somewhat greater than 6 feet. That seems entirely possible that somebody might hit a volleyball from that height. You're probably not going to get the most devastating slam out of this height. That's actually not very high. I guess not even higher than the net. So this is not a good way to win a point in volleyball, but it's certainly something that somebody might do on a volleyball court. On the other hand, suppose that the answer had come out to be about 0.2 meters. That's only 20 centimeters. Well, it's possible you could hit the volleyball from 20 centimeters, but that's starting to seem suspiciously small. And this would seem very suspiciously small and be a strong indication that we'd made a mistake in our solution. How about 21 meters? If we'd gotten an answer of 21 meters, well, that would be about 21 yards. If you think about how long 21 yards is on a football field, you can see that would be a ridiculously high height for somebody to hit a ball from. No one could reach or jump that high, and that would be a strong indication that you had made a mistake somewhere in the problem, which could be very useful if this was an exam problem. That gives you a second chance to go back and fix your mistakes. Okay, so this seems like it's roughly in the ballpark of something that seems fairly reasonable for a height that someone might hit a volleyball from. Okay, I know that you might find it difficult and time-consuming to go through that process of asking if the answers make sense, but I encourage you to do that. You'll get better the more you practice, and it'll give you a better understanding for the material and help you to maybe catch some mistakes on the test. So we made our checks. We saw that we'd answered the right question. We answered all parts of part A anyway. Our answer made sense. We included the units. This step is not relevant here because our answer is numeric, not symbolic on this problem. So to review, the most important thing that was crucial for getting this particular part A correct was the negative sign on the y component. And I talked about the techniques you can use to get that correct. Now we're not done, so let's move on to part B. So let's figure out what the question is for part B. Remember, a good way to do that is by using a question mark and trying to figure out the correct symbol. Well, this problem is asking us for this symbol, boldface V. Boldface V. That's the symbol that is used for vectors in textbooks. However, it's not that easy to write boldface on your paper. So how are we supposed to handle that? Remember, we want to use the exact right symbol. Well, the convention is that instead of using boldface, we use an arrow. You've probably already seen this in your class. All right, so you should know V in boldface means the same thing as V with an arrow. They both mean the complete vector velocity. Velocity considered as a complete vector. So that's what the question is asking us to figure out, the complete velocity vector. And we need to express that using the unit vectors. So I'll talk more as we go on about how we use the unit vectors to do that. Basically what this means is that we need the x and y components of the velocity. They want us to express the velocity using the x and y components. So what do we need to answer this question? We need the x component at time 1, and we need the y component at time 1. By the way, this is the symbol the problem told us to use, but we should notice that a more specific symbol that we could use for that, well, another symbol we could use for that is V1, because time 1 is when the ball is going to hit the ground. So what this is really asking us for is the vector velocity at time 1 when the ball hits the ground. All right, so we're gonna stick with this symbol because this is the symbol the problem used, but we should recognize that that's the same as what we would usually call V1. So we need the x component at time 1 and the y component at time 1. That's what we need to express this in terms of unit vectors. But wait, remember, the horizontal velocity is always the same, so we don't need a time subscript for the horizontal velocity. So now these are the symbols for what we need. Again, as we've discussed, in projectile motion, the vertical velocity is changing at different points in time, so we need a time subscript to report the vertical velocity. But the horizontal velocity is constant at all points in time. So we don't, the same at all the points in time along the parabola, so we don't need to use a time subscript for the horizontal velocity. So these are the symbols for what we need. And then, wait, we already figured out Vx, didn't we? Here's Vx. Here's where we originally figured out Vx. It's positive 16.4 meters per second. So we're already halfway done, so to speak. We need to know what Vx is to answer this problem, but we actually already have that. We already knew Vx, 16.4 meters per second. So all we're going to have to figure out here is the vertical velocity at time 1. So notice what we did here. Where did this number come from? This number is the horizontal velocity at time 0. 16.4 meters per second is the horizontal velocity at time 0. But since the horizontal velocity is constant, 16.4 meters per second is also the horizontal velocity at time 1. The horizontal velocity here is the same as the horizontal velocity here because the horizontal velocity is constant. So we can use the horizontal velocity that we figured out from the time 0 velocity and we can also apply that horizontal velocity at time 1. Can we do the same thing with the vertical velocity? Can we take this number for the vertical velocity at time 0 and plug it into time 1? Absolutely not, because remember, vertical velocity is changing. So there's absolutely no reason to think that the vertical velocity here is the same as the vertical velocity here. The vertical velocity is changing. In fact, it should be obvious that this vertical velocity will be bigger in magnitude than this one because objects speed up as they're falling. All right, so we still need to know this number, and we don't know that number yet. Remember, it's nice if you can build the question into the sketch. So we could say here that what the question is asking us for is the vector velocity at time 1, which we're going to symbolize in this problem by v, because that's the symbol the problem gave us. And we can say that what we need is v sub 1y. We also need vx at this point, but we already figured that out. Maybe I'll build that into the sketch here anyway. Okay, so I went ahead and built a lot of extra information into this sketch to make things as clear as possible. So here are the velocity components at time 0. We figured out that the velocity components at time 0 were 16.4 and negative 4.4 meters per second. So I've written those two velocity components here at time 0. And then we know that since the horizontal velocity is constant, this Vx at time 0 is the same horizontal velocity at time 1. So I copied that horizontal velocity over here as the same at time 1. On the other hand, since the vertical velocity is changing, we can't copy this number over. The vertical velocity at time 0 will be different than the vertical velocity at time 1. So this is the piece of information we still need. We still need to figure out this component. In order to figure out the vector velocity at time 1, we're going to need to know its two components, and there's one component left. Unfortunately, when I first recorded this video, I made a mistake in the symbols that I wrote down here, and I didn't notice that mistake until after I'd already finished recording the video. So I'm going back to re-record a little bit right now in order to fix that mistake. I'm always telling you in these videos that you should try hard to use the exact right symbol at each point, and I didn't follow my own advice here. I used an incorrect symbol. Did you catch that already? Have you already noticed which was my wrong symbol? Perhaps you should pause the video and see which of the symbols I wrote down here is not correct. I hope you gave that a shot. Maybe you'd already noticed it. Well, remember the question is asking us for v. This symbol, which stands for the overall vector velocity. And we can say, to be more specific, that that's v sub 1, the overall vector velocity at time 1. But again, remember, they're asking us for the overall vector velocity. That's implied by the wording here. So I made a mistake when I included the y subscript here. That's a mistake. The question is not asking us just for the y component. That was my mistake. The question is not asking just for the y component. The question is asking for the overall vector velocity at time 1. So that was my mistake. This is correct. We need to know the y component of the velocity at time 1 in order to figure out the overall vector velocity. But this is not what the question is asking us for directly. This is what the question is asking us for. So to repeat, there should not be a y subscript on this symbol. I made a mistake and I should not have included the y subscript on this symbol. All right, so remember, always make a strong effort to use the exact right symbol, including the exact right subscripts. But however hard you try, sometimes it's inevitable that we'll make mistakes. And I did make a mistake the first time I recorded the video in this particular symbol. So unfortunately, since I didn't catch that mistake until after I finished the video, you'll still see that mistaken symbol in most of the rest of this video. But I hope that you remember that this is that these are the correct symbols for what the question is directly asking us for. Did you catch that mistake on your own? Did you notice that this symbol was wrong when you were watching the video? If so, that's great, and you're making strong progress at always paying close attention to the exact symbols. And if you didn't notice that I made that mistake, then you should work harder to pay close attention to those symbols and subscripts. It looks like I need to keep working at that myself since I had made that mistake at this point myself. Okay, you don't necessarily have to write this much information in your own sketch when you solve the problem, but if you thought the problem was tough, if you thought this was a difficult problem, then maybe it would have been helpful to write this much information into the sketch in order to think more clearly about what you knew and what you still had to figure out. Remember to make a big sketch so it has plenty of room to fit as much information as you eventually want to build into it. Don't try to cram all the information into a tiny sketch. Make as large a sketch as the space will allow. Okay, now we should identify the question in this sketch. Now this was the question from part A, and now we're working on part B, so this is no longer the question. And in fact, we should always build new information into the sketch. Now that we know this 2.17, I should build that information into the sketch. This H is 2.17. And we've built the new question into the sketch over here. Here was the old question. Here's the new question. By the way, you can see that as it turns out, the distances in our sketch are clearly not to scale. This number is more than twice as big as this number, but this distance doesn't look more than twice as big as this distance. But that shouldn't worry us or make us think that we made any mistakes. We drew this entire sketch ourselves, and in particular we drew the amount of curving in the parabola ourselves freehand, so there was no particular reason to think that the distances would come out to scale. Just drawing this angle to scale, simply drawing to this angle to scale, is not enough to guarantee that the distances will come out to scale. And in fact, they didn't. So let's see. We've identified the new question with a question mark and symbols, and we built that question into the sketch, and we also built what we needed to answer the question into the sketch. Can we keep the same initial and final positions as for part A, or do we need different initial and final positions? Well, I think we're still interested in the same 2 points as before. We're still interested in time 1 because, for one thing, that's what the question is asking us about. And we're still interested in time 0 because we know a bunch of information about it. So we're going to stick with the same initial and final points as before. And that means that we can use the same setup as before. We can continue to work with this same setup because we're sticking with the same initial and final points that the setup was based on. So here's our previous setup. Now we need to try to build the new question into our setup. So this is no longer the question. And in fact, we should build our new information in now. Now we know this 2.17 number, so let's try to build that in. 2.17 meters is what we figured out in part A. So we can build that in here. So remember, actually, none of these symbols will completely answer the question because none of these symbols is the complete vector velocity. But remember, what we need to answer the question is v final y, the vertical velocity at time 1. So I can put the, so I won't label this with a question mark, but I'll say this is what we need to answer the question. We need to know v sub 1y. When we know that, we'll be in good shape to answer the question. Now, let me point out a mistake that I see students make sometimes. I already mentioned this mistake in the previous video. Some students might say that after the object hits the ground, it'll be resting, and therefore the velocity should be 0. That's a mistake. But some students think that the final velocity is when the object is resting on the ground, and they mistakenly plug in 0 here. I already explained in the previous video why that is incorrect. What we want here is the vertical velocity when the object hits the ground, or as the object hits the ground, not the velocity after it's resting on the ground. And when the object hits the ground, it's actually moving at its greatest speed, not at a speed of 0. So it would be a mistake to plug in 0 here. Remember, we're going to plug these numbers into our projectile motion equations. So we need a velocity. So we can't plug. We shouldn't plug in what happens when the object is at rest, because once it's at rest, it's no longer experiencing projectile motion. So that's what they mean when they ask the velocity when the ball when it hits the ground. So if you were doing this problem on an exam and you said, well, when the ball hits the ground, it'll be at rest, and therefore the velocity is 0. The professor will just call you a smart aleck and give you maybe 0 points for that, because that's not, so that's a wrong answer. That's not what the professor is going for here. They don't want you to just say that it will be at rest after it hits the ground. They want you to figure out the velocity as or when it hits the ground, which is quite different from being at rest. Okay. So notice that in this case, none of these symbols would completely answer the question. So I didn't use a question mark. Instead, I indicated what we needed from the setup in order to answer the question. We needed v final y. I think we've really already completed this step, so now we're again ready to pick an equation. Now clearly here we've done as much work as we can with the x component. There's nothing more to figure out on the x component, so we need to stick with the y component. And we should be in pretty good shape here. Now we know 1, 2, 3, 4, 5 numbers. With 5 numbers, there's 2 equations we can use. We just have to use either equation that includes v final y. We have to pick either equation that includes v final y. So we could pick, let's see, are there 2? Yeah, here's an equation that we could use that has v final y, and here's an equation we could use. This equation wouldn't help us because it doesn't include v final y. You could use either of these 2 equations. Either is fine, but this one looks simpler, doesn't it? So let's use this simpler equation to find v final y. So I'll start by writing that equation down. So that's going to be v final y equals v initial y plus a sub y delta t, and use your setup to plug in the numbers that we need. V final y we don't know, but we're going to use this specific symbol v sub 1y for that. V initial y is our negative 4.4. Again, it's important that we know that this number is negative. A sub y is negative 9.8. And delta t, that's a number we figured out previously, 0.354. Remember that you should write the general formula before you plug in. Don't go straight to here, write this line first. Now we're ready to use our calculator. And again, if we've written this correctly on the page and we type it into the calculator, exactly the same as on the page, we can do it in one step on the calculator. Before I hit enter, I need to double check that I've entered this correctly. I'll round this off to 3 digits. Because this is a 9, I'll round this up to a 7. Remember to put in units. Now, we should definitely stop and ask whether this makes sense. It should jump out at us that this number came out as negative. Does that make sense? That v1y would be negative? Yes, it does make sense, because when the object hits the ground, it's moving downwards. And downwards is our negative direction, our negative vertical direction. So it makes sense that this was negative. And in fact, suppose this number had come out to be positive 7 meters per second. Then we would have known we made a mistake, because then the math would be saying that the object was moving up when it hit the ground, which wouldn't make any sense. All right, so it makes very good sense that this came out to be negative. That's what we should have expected. Just like the initial velocity was negative, the initial vertical velocity was negative, the final vertical velocity should also be negative because the object is moving downwards at both points. So that makes good sense. Okay, well, didn't we say that we were going to need v1y to answer the question? And now we know it. So now we should be in good shape to actually answer the question. So remember that the question is asking us for v, which is the vertical velocity at time 1. So let's see if we can figure that out. v is the vertical velocity at time 1. And the problem told us to express that using the unit vectors I and j. Do you know what those are? So you should know that I has a magnitude of 1 and it points in the positive x direction. And you should know that j has a magnitude of 1 and it points in the positive y direction. Okay, now again we have a problem, which is that these are vectors, so they're written in boldface here, but we can't easily write boldface on the page. Now you might think that we should write them with arrows. Didn't we say that arrows is our replacement for boldface? Well, that's usually true, but not for the unit vectors. Unit vectors have a separate notation. The notation for a unit vector is a hat. So instead of using boldface, we're going to use the hat to represent these unit vectors. Now you can see that I is about the x direction, so we're going to use I to express our x component. We already knew that the x component was 16.4, positive 16.4. So our x component here is positive 16.4 meters per second. That's our x component. So in the unit vector approach, that multiplies times I. And now what we're going to do is add the y component at time 1. Well, we just figured that out. The y component at time 1 is negative 7.87 meters per second. And we need to multiply that times j hat. That's how to express this overall vector in terms of the unit vectors. Okay, so that's our answer. Now we've expressed v in terms of the two unit vectors. So in case you didn't know, let's summarize how to express an overall vector in terms of the unit vectors. So you can see that first we write the x component. And then we multiply that by I hat. That makes sense because I hat is in the x direction, so it makes sense that that's associated with the x component. Then we add, to that we add the y component. Here's the number that we had gotten for the y component. And since this is the y component, it should make sense to you that we're multiplying that by j hat, because that's the unit vector that's associated with the y direction. And that's all there is to it. That's how you express an overall vector in terms of the unit vectors. X component times I hat plus y component times j hat. You should, just like with any of your answers in physics, still include the units. And notice it's very important for this notation to include a plus. This is one single equation. This is one single equation. So, for example, this should not be a comma. When we use the unit vectors, we're not just expressing each component separately. We don't want to separate them. We want to add them together in a single expression that together completely represents the overall vector. So this is the correct way to do it. Again, this is how you express an overall vector in terms of the unit vectors, which is something that you see that you might have to do on your physics midterm. By the way, you could turn this addition into a subtraction, because adding a negative is the same as subtracting, but I recommend that as a beginner you should not do that. As a beginner, it's better to express the overall vector as an addition. You'll have a better understanding of what this notation means if you keep this as an addition rather than turning it into a subtraction. Why does this notation make sense? Why is this a good way to represent an overall vector? Well, this term is a vector that represents the x component of the velocity. And this term is a vector that represents the y component of the velocity. And if we add, so if we add the vector for the x component, and if we take the vector for the x component and we add that to the vector for the y component, then the resultant is a new vector that does represent the overall velocity. That's why this notation is a logical way for us to represent the overall velocity. Let me briefly point out a couple of wrong ways to write this. What are some wrong ways you could write this? First of all, well, this would be wrong. Can you see what I did wrong here? Obviously, we can't leave out the unit vectors. The whole point is to use the unit vectors here. This is not correct. One way you can see this is not correct is that now the right-hand side just has scalars. It just has numbers. If you just add ordinary numbers, you can't completely represent a vector because vectors have directions. If we want to completely represent a vector, we have to use vectors on both sides, and that's the purpose of these unit vectors. So this would be a wrong way to write it. You have to include the I and the j. Something else that you can't do is you can't actually do, you should not do the calculation 16.4 minus 7.87. We don't do that calculation. That's, this calculation. We don't do the calculation 16.4 minus 7.87. That's not what this is telling us to do. You can't do that calculation. That would come out to be about 8, but that would again be wrong. If you had the expression 16p plus negative 8q, I hope you know enough algebra to see that you can't just do 16 minus 8 and get an 8 out of that. That would be wrong. You can't just subtract the 16 and the 8 here because these are unlike terms. Because this has a p and this has a q, they're unlike terms, and that means that you don't combine the 16 and the 8 directly in a subtraction. Well, similarly, these are unlike terms. This term has an I hat and this term has a j hat. Because they're unlike terms, we don't combine these numbers directly. That's again why this is wrong. This is wrong because it suggests that we could combine the numbers directly. Maybe I'll erase this to show that it's wrong. When you have unlike terms, you can't combine the numbers directly. You simply have to leave each term separate and just show that you're adding them. And similarly, because these are unlike terms, we can't combine these numbers directly. We just have to write out each term separately and show that we're adding them. So here's a correct way to express the overall vector in terms of unit vectors, and you should try to avoid some of the incorrect mistakes that I just demonstrated. It might help you to think of this as an addition of unlike terms, such as 16p plus negative 8q. This is basically 16i hat plus negative 8j hat if we round off a bit. So now we've learned how to express an overall vector in terms of the unit vectors. We know how to answer that type of question if you see it on the test. Here's our answer to part B. Now let's do some of our standard checks. We should check that we included units, and yep, this answer does include units. We should check whether we've answered the correct question and whether we've finished answering the question. So the question here was asking us for v expressed in terms of the unit vectors. So we did answer exactly what they were asking us for, and we did that correctly. What would I mean by, what would be answering the wrong question? Well, later in this series, you'll see other problems that might ask you to express the magnitude and direction of v. If the problem had asked us for the magnitude and direction of v, then this would not be the right way to express our answer. So that's what I mean by answering the right question. Some questions might ask you for the magnitude and direction of v. Other questions might ask you to express v in terms of the unit vectors. Well, those require two different answers. So you always want to double check to make sure that you're answering the right question, the question the problem actually asked you. And I think we've also answered all parts of the question now. But we do want to pause and ask, does this answer make sense? Well, I think we've already confirmed that the plus and the minus sign make sense. When the object hits the ground, it'll be moving to the right and down. So it makes sense that this component is positive to the right and this component is down, negative. So those two parts do make sense. What else can we check here to ask if this makes sense? Well, we can think about the sizes of these numbers compared to our previous numbers. So notice that the x component here is 16.4 meters per second, and that's the same x component we used at time 0. Does that make sense? Yes. It makes sense that we're using the same x component at time 0 and at time 1, because in projectile motion, the horizontal velocity is constant. So it makes sense that the size of this number is the same as this x component at time 0. Remember, this is the velocity at time 1 when the object hits the ground. Now, what about the size, the magnitude of this number, 7.87? Notice that that is bigger than the velocity here. Maybe we can go ahead and build this all into the sketch to help us ask whether this all makes sense. Build each new piece of information you figure out into the sketch. Well, we now know this y component, so this is no longer something that we need. Now we know that v1y is negative 7.87 meters per second. Now notice that that is considerably bigger in magnitude than v0y. So does it make sense that this number has a bigger magnitude than this one? You might want to pause the video and think about that. Well, it totally makes sense. As an object is falling, it makes sense that its vertical speed will increase. Remember, the only force here is the force of gravity, and gravity is pulling downward on the object, trying to speed up its vertical speed as it falls. So yes, this makes good sense. We started with a vertical speed of 4.4 meters per second, and then gravity sped up that vertical speed to 7.87 meters per second. If this number had come out to be, say, -3, if this had been -3 meters per second, do you see we would know we made a mistake, because this wouldn't make sense. There's no way that the object would have a slower vertical speed when it hit the ground than when it started falling. So this answer would be a clue that we'd made a mistake somewhere along the way. So it makes good sense that this number is bigger than this number. Did you think about that when you solved the problem? Did you compare these numbers? That would be a good thing to try to do. Compare different numbers that are comparable to see if your answer makes sense. That'll give you a better understanding of what you're doing and maybe help you to catch some mistakes. On the other hand, again, it makes sense that these two numbers are the same because gravity is vertical and therefore it doesn't affect the horizontal speed. Gravity is vertical and so it has no effect on the horizontal speed. That's why those speeds are the same. Okay, so yeah, I think that these numbers do make good sense. These are fairly logical numbers. There's other things I guess we could do to check if this makes sense, but I think that's good enough for this video. Notice how it's good to build this new result into the sketch. That's what gave me the idea to compare this number with this number to see if they made sense. Always try to build each new thing that you figure out into your sketch, and that might help you to see whether your answers make sense. I'll just take this opportunity to remind you one more time, as I mentioned earlier in the video, that the first time I recorded this video, I made a mistake in this symbol. This symbol is not correct. The question is asking us for the overall vector velocity, not the y component, so I shouldn't have included the y subscript here. This is correct. We need to know the y component in order to solve the problem, so this is correct. But I shouldn't have used the y subscript here because this is supposed to represent what the question is directly asking us for. I wrote that correctly up here. So this was a case where I failed to use the exact right subscript, so I guess I'll have to keep working at that. Okay, so we've completed these checks. We made sure we answered the right question. We've answered all parts of the question. Our answer seems to make sense. We included the units. And this step is not relevant because we have a numeric answer, not a symbolic one. Now let's review what are the key lessons and techniques to learn from this problem. First of all, remember that the scratch work and notation that I'm modeling in these videos is the scratch work and notation that I'm hoping that you will imitate in your own solutions as much as possible. So try to make large, careful sketches, and as the problem proceeds, try to plug as much information as you can into our sketch. Notice that by the end of our solution to the problem, we had plugged a lot of information into this sketch, and I think that's very helpful in solving the problem, especially if the problem is giving you some difficulty. Remember to label all the numbers that you write down in your sketch and elsewhere. Don't just write down a number, write down the symbol that labels that number. I think we saw in this problem how important it was to use this setup for solving problems. So remember that the setup involves two columns. Here's what the x component column looks like, and here's what the y component column looks like. It's good to keep all your work on the x component on the left and all your work on the y component on the right. Notice that in this more complicated problem, we actually had to use two y equations. First we used this y equation, and then when we went on and used this y equation, but I tried to put them both in the left-hand column to keep the work organized. Again, on this problem, one of the key issues was the negative sign on the y component. So remember, we've discussed a lot of techniques you can use to make sure that you notice when vector components are negative. That's important for succeeding in physics. We also learned how to deal with this idea of expressing a vector in terms of the unit vectors. So remember, this example summarizes how you express a vector in terms of the unit vectors I and j. Here's some of the important ideas that we used in solving this problem. Let me emphasize that we succeeded here by thinking in terms of components, and our final sketch really shows that, I think. So notice that we were given the magnitude of the initial overall velocity, and then we took that number and we broke it into an x component and a y component. And then the problem in part B was asking us about the velocity at time 1. And in order to think about that, we thought about the components at time 1. We were able to quickly write down the x component at time 1, because that was the same as at time 0, but it took us more work to figure out the y component at time 1. And then I guess actually we eventually worked that out here. So now here we have both components at time 0, and here we have written both components at time 1. So now this diagram illustrates pretty well how the way we thought about the velocity at time 0 and at time 1 was by thinking about the x and y components at time 0 and the x and y components at time 1. That's a great illustration of how thinking in terms of components is absolutely integral to succeeding in physics. Of course, we commonly used here the idea that for projectile motion, the vertical velocity is changing, but the horizontal velocity is constant. That's why we had the same Vx at time 0 and time 1, but we had different Vy's at time 0 and time 1. Now let me remind you what I've said before. Another crucial skill is always making a strong effort to use the exact right symbol, including the exact right subscript. I said you should be modeling your notation on the notation I use in the videos, and part of that is making a strong effort to always label each idea and number that you're writing down with the exact right symbol. I think that's a very hard job, and here's an illustration of why that's a hard job. Here are some of the symbols that we used in this problem related to velocity. These aren't even all the symbols, but these are some of the symbols we used in this problem that were related to velocity. So let's do an exercise here. Would you please pause the video and try to write down exactly what each of these symbols stands for? I really encourage you to actually do that exercise. Pause the video and write down exactly what do each of these symbols that we used in this problem stand for. Well, I hope you actually tried that exercise, and here are my answers to that exercise. So you should pause the video again and try to understand why each of these interpretations is correct. So one thing that we saw that was important here was that when you're doing the SOHCAHTOA equations, it really helps to have separate symbols for the complete component and for the magnitude of the component. So remember that when we write these symbols in absolute values, those stand for the magnitudes of the components. And when we write the same symbols without the absolute values, that stands for the complete component, including a plus or minus sign. Do you remember what a magnitude is? So as we discussed in the previous video, A magnitude is a number that could be positive or negative, but that can't, A magnitude is a number that could be positive or zero, but could not be negative. And you can see that absolute values are a good way to indicate that for components, because absolute values can't be negative. Do you remember how that came in handy here? That came in handy in the SOHCAHTOA equations. Remember, the SOHCAHTOA equations don't tell you the sign on the component. So to remind ourselves of that, we use absolute value symbols when we're working through the SOHCAHTOA equations. That reminds us when we get this far that we're not done yet. We've only figured out the magnitude, and there's still one more step to write the complete component that includes the plus or the minus sign. And only once after the SOHCAHTOA equations, all we know is the magnitudes, and we indicate that by using absolute value signs. Then at this point, after our extra step, now we know the complete component, including the plus or minus sign, and only now then do we write the symbols without the absolute values. The plus and minus sign does not come from the SOHCAHTOA equations. Where does it come from? It comes from the arrows on the legs of this triangle. Okay, so I hope you can see how it really does come in handy to have separate symbols for magnitudes and complete components, because that helps you to distinguish what tasks you have to accomplish when you're breaking a vector into components. Now here's some of, in this problem we had to focus not just on time 0, but also on time 1. Here's some of the symbols we used for time 1. Notice that these two symbols mean the same exact thing. This symbol in boldface means the same as the symbol with an arrow. In the textbook it's usually written in boldface, but on paper you would usually write it in the arrow. These two things mean the same thing. By the way, notice how subtle it is. Do you see that these do not mean the same thing? These symbols do not mean the same thing because this is in boldface and this is not in boldface and does not have an arrow. This symbol does not mean the same thing as this symbol. In boldface, or with the arrow, it refers to the complete vector velocity. But when it's written like this, without an arrow and in regular type, it's not the complete vector velocity, it's just the magnitude of the vector velocity. So that is, this symbol does not reflect the direction. This symbol does not reflect the direction of the velocity, whereas this symbol does reflect its direction. That's a pretty subtle distinction, I think. Notice I used Vx both here and here, even though it meant the same thing in both places, just because that same Vx was relevant to both time 0 and time 1. One more thing that I think you might find confusing, remember that these bold-faced or arrow symbols refer to the overall velocity. But when we expressed that overall velocity, we used the components to express it, didn't it? The arrow means this is the overall vector velocity. If it's the overall velocity, is it contradictory to use the components? Well, no. As we discussed earlier, this term by itself would be a vector that represents the x component. And this term by itself would be a vector that represents the y component. But if we take a vector that represents the x component and then we add to that the vector that represents the y component, then the resultant that we obtain from that addition is a new vector that does represent the overall velocity vector. So there's no contradiction between saying that we used the components on the right to express the overall vector on the left. It does stand for the overall vector, but one way to describe the overall vector is to say that you could construct the overall vector by adding a vector that represents the x component and a vector that represents the y component. That's a little bit of a subtle idea, but I hope it's not too confusing. Okay, so this is a good illustration of this point that I'm making. It's crucial for your success in physics to make a strong effort to always use the exact right symbol, but it's also really hard. It's really hard, right? Look at how many different symbols we had just for velocity on this problem. Well, the way to get better at this is to make that effort. Don't be lackadaisical about your symbols or your subscripts. Keep making a strong effort to use the exact right symbol, and the more you practice that skill, the better you will get. And the better you get at that skill, the more difficult problems you'll be able to adapt to. When a question is really easy and very similar to the questions you've seen before, maybe you'll be able to get by even if you don't have the exact right symbol. But the harder the problems become and the more you have to adapt to each new problem, the more important it is to be able to come up with the exact right symbol. So keep working on practicing that skill. Keep asking yourself if you're using the same symbols in your work that I end up using in my solutions. Let me remind you that one of the most common mistakes in physics is confusing the concepts. For example, you don't want to confuse the magnitude of a component with the complete component. You don't want to confuse x components with y components. Obviously, if you plug an x component into a y component equation, you'll get the wrong answer. You don't want to confuse time 0 concepts with time 1 concepts. Obviously, if you plug in a number that represents time 0 when the equation requires time 1, again, the equation is going to give you the wrong answer. Don't confuse concepts that are about overall vectors with concepts that are about vector components. So there's many different potentials for confusing the concepts, and you have to work hard not to do that. As I talked about in the previous video, a good way to not confuse the concepts is don't use the word it. Don't say that it is negative 7.87 meters. Say that v sub 1y is negative 7.87 meters, or that the vertical velocity at time 1 is negative 7.87 meters. Don't say that it is 16.4 meters per second. Say that Vx is 16.4 meters per second. If you always name or label each number that you're dealing with, you're much less likely to confuse them. But if you don't name and label them, and if you just call them it without a label, then you're very likely to plug each of these numbers into the wrong places in your equations. You can see it's easy to plug them in the wrong place because they have the same units, right? All of these numbers here, these have the same units, but they go in different places in your equations. If you're referring to a number as it, you might easily put it into the wrong place in your equations. But if you always label it with a name or a symbol in your mind and on paper, you're much less likely to end up confusing the concepts in that way. So that's something else to keep working on. So be tough on yourself. When you're thinking about these ideas in your head, don't let yourself just say the number. Always try, even mentally, to label the concept with a symbol or a interpretation. Okay, well that was another long and slow and repetitious video because I want it to be as helpful as possible if you're finding the material to be difficult. As you go on to the next video, remember that if you're finding the videos to be too slow, you can always use the solutions document as a supplement or replacement to these videos. And of course, you can always just skip to the particular parts of the videos that are of interest or of help to you. Now would be a good time to move on to the next video in this series and to keep practicing your projectile motion skills. Remember that when you try that problem, you should be trying to use the systematic techniques and process and notation that we illustrated in this video. You don't want to wing it. You don't want to have a different method for each problem. You want to do each problem as much as possible in a similar approach. Hopefully the approach that we're demonstrating in these videos. Okay, so I'll see you in the next video.